the fundamental theorem of calculus for line integrals. And in the setup for this theorem, there is not really a vector field. There's a function f. So let's let this f be a function whose gradient is well defined on a domain D. This is just like saying it's differentiable because its gradient is defined and well behaved if the derivatives are well behaved. So if P and Q are points in this domain, maybe I'll draw a picture here. If P and Q are points in the domain, and C is a path that goes from P to Q, then the difference between the endpoints of that path is a line integral of the gradient of f. So remember, this was started out as a statement about a function, a real valued function f. And what we've got here is a net change and an integral of, well, the gradient, which we can think about as a rate of change. Right. And how does this connect to our conversation? Well, this is a vector field, right? So a line integral of this vector field, specifically along a path between those 2 points, that will give us the net change between those 2 points. Now notice the points P and Q are defined, but C is a path between them. Any path. So this is telling us we can sort of ignore what happens in between. Well, that's not quite right, but it doesn't matter how we get from P to Q, the answer will be the same. So let's look at a picture. We'll work out some examples, and then we'll talk about some of the implications of this. So in this picture, what I have here is, well, the white arrows are the gradients of some function f. And then we see the contour plot of f along with some labels. As we expect, the arrows are pointing perpendicular to the contours everywhere. So let me find a color that will show up on here. Mabel will be really happy if I use pink. So let's put the point P and the point Q on the map. And let's say I draw a path called C1 that goes from P to Q. Well, let's see. What does the fundamental theorem of calculus tell us? It says, now I'm reversing the order of the equality here, but it says that the line integral along that path C1 through the vector field should be the same as the difference in the function output between those 2 points. Well, I picked these pretty carefully to lie on contours. F of Q lives on this contour where the output of f is 6. And f of P lives on this contour where the output of f is 2. So the result of that line integral, 4. And what's better doesn't matter how I get from P to Q. I could have taken a path with lots of detours, gone up and around and back down. 4. The answer is still 4. Because, oops, I'll call this C2. According to the fundamental theorem for line integrals, it's the endpoints that matter. One more. Let's illustrate what we saw, or what we said about a circulation integral. Let's call this path D. Oops. This is a gradient. We could call this big F, but I haven't named it that way. So according to the fundamental theorem of calculus, this should be the function evaluated at the endpoint, let's call it R, minus the function evaluated at the start point, which is also R, because it's a closed integral, a closed loop, which is 0. And there's nothing special about this curve D that I've drawn. This could be any closed curve. So let's record a few important notes. One is that an immediate consequence of the fundamental theorem of calculus for line integrals is that gradient fields are path independent. Right, the fundamental theorem tells us if you want to compute the line integral of this gradient field along a curve C, all you need to know is the endpoints. So any curve C that goes between those endpoints will get us the same answer. Now, this is not obvious, but it turns out also that all path-independent vector fields are gradients. This is kind of similar to maybe what we would call the fundamental theorem of calculus part 1 or the accumulation theorem. There's this theorem that looked like this, that the derivative of an integral that has a variable as the upper bound is just that function that's on the inside. And maybe it was unclear why this was useful. It tells us something about accumulation and the rate of change of accumulation, but a big implication here is that every function, every well-behaved function has an antiderivative. Specifically, whatever this function f is, this thing inside of the d dx is the antiderivative. Now, it's not always a nice thing to write down. We can't always find an algebraic formula for the antiderivative, but that's how we can build an antiderivative of a function. And we can do the same thing sort of here. So if you're curious about it, we can talk about it. But you can use this idea of a line integral to actually build the function for which it's a gradient. And actually, let's give that function a name. Well, it has a name. If f is a vector field and f is the gradient of some function little f, so that's a real valued function, we say that little f is a potential function for big F. And the word potential, again, comes from physics, talking about potential energy. All right, so this is where we'll stop this video. In the next one, we'll talk about how we can find a potential function and if a potential function always exists.